It is time to start Chapter 9, Numeric Integration. We will be going from ultra basic Riemann sum type integrations of rectangular elements for a whole region down to Simpson's 3/8 rule and into Gauss quadrature a little bit. But first of all, I want to go through the first couple pages here very quickly because suffice to say they start talking about whole region integrals, the difference between closed and open methods, just different things there. But they start discussing these full region integrations and how to approximate the region, looking at it in a whole one big chunk. Never do that numerically. The entire principle of numeric integration is you'll be doing these sub-interval type operations, these composite integrations, such that each interval takes its own small approximation of what's happening within its bounds. And you add up all these smaller chunks to form up the actual area under the curve, which is the easiest way to view a numeric integral. You're adding up all of the area under this curve, and the better the estimate of the boundary of that curve, the better your integral estimate is going to be. So overall, the first method here, rectangular, ultra, mega simple. You take the functional value at every one of your x reference locations, whether that's evaluating the function for every x area of interest or whether it is operating off a set of given data. You take that functional value, you multiply it by the distance between the next element and the element you're at, and that's kind of your side steps. That creates this rectangular region with an area you can easily calculate. Very easily, because you take, well, the functional value times your horizontal component of the rectangle, and that forms an area. So you say chunk 1, the integral of area 1, the integral of area 2, the integral of area I. You sum all of those up, you end up getting this summation from 1 to n, where n in this case is not the number of points, but it is the number of intervals. That can be confusing. There were a few questions earlier about that. N in the textbook is number of intervals between points. So if you have 10 points, you have 9 intervals. If you have 8 points, you have 7 intervals, etc. So just keep that in mind. That's the book standard. They sum up the functional value at each point and multiply it by the distance between the next point and the point you're at. So this means that it is variable enough here that you do not have to have an equal step size. The fact that it's accounting for the difference in the distances between points means that h, your step size from one point to the next, can vary. This is most easily represented in a big summation. So if you say I of f, this is, by the way, the rectangular integral form from a to b of the function f of x dx. H actually falls out in front of the summation because it's constant throughout. It's like a constant of integration. You can pull it straight out front. So from I equals 1 to n for every region, you evaluate the function at x of I, and that's it. This is a massively simple estimation method. It can be a little bit inaccurate, and the way you solve that, or the way you account for the inaccuracy of that simplistic methodology, is to just use a whole lot of subdivisions. You slice this into very small time steps, spatial steps, whatever the dimension of interest is, and by doing that, you minimize the error. You minimize the amount of area that's lying unaccounted for underneath the curve in the regions you've cut it into. But the other way to handle this without going into a billion little sub-elements is to improve your methodology, improve the algorithm calculating the derivative, because you don't always have the luxury of manifesting more points or manifesting more subdivisions in your solutions. Thus steps in the midpoint method. It's a little bit better. They say instead of sampling your function at the endpoints, we'll sample it at the middle, so that way a little bit of your error is in excess and a little bit of your error is a detriment to the true area under that region of the curve, so that hopefully things more or less average out. So that it's the functional evaluation. Each little step would be the functional evaluation at a location of the left side plus the right side divided by 2. So the average distance, it's just the midpoint, multiplied by b minus a. So b minus a is the distance between the two ends, the two sides. So that becomes your step. So again, it's a rectangular method. It's a width and a height. Height defined by the functional evaluation of at the midpoint, and the width divided by b minus a. So this can be put straight into a similar integration as before, where you do, again, draw out the step size, which is the same throughout, go from points 1 to n for a number of intervals, and at every single point you take the x location you're at plus the x location next in line divided by 2. What this ends up producing is just a series of composite rectangular elements all sampled at their midpoints. And again, like you say, you sum it all up, multiply by the size of your step, and that would be the average integral value. It's a bit better method than just the pure rectangular, but we're still not to kind of that nice inflection point in complexity versus payoff, because the next method is just about the same, but a little bit easier to code and implement, which is really just called the trapezoidal method. If you look formulaically, this method and that method, the two algorithms are very similar. You take the function at the left-hand side and add to the function of the right-hand side, divided by 2, multiplied by your step size. So the trapezoidal method and the midpoint rectangular method are virtually identical. The difference is they're actually sampling the function of the midpoint here, where here they are doing all the functional evaluations at the same end points, and they're just averaging the value. So it's a semantics type error, or not error, but difference between the two. And of course, this first describes a one region example, and you would always do this in composite. That's the entire point of numerics. So you would take the function of x, all these subintegrals, and it ends up manifesting itself as in the total summation in this form. So it's 1/2 the sum of the left-hand functional value plus x plus 1 added together, all multiplied by the distance between the points. So if you have non-uniform step size, equation 912 would be the ticket. That's how you'd have to look at the entire domain. If you have a uniform step size, then equation 913 comes in. You can see there was some confusion in questions earlier about the definition of n, and the index has to change whether you consider n to be the number of points or the number of intervals. The book's formulation is number of intervals. So what's interesting is that now it's not just some simple summation when you put it into constant step size h. Something different happens. The first point, f of a, so that's the leftmost point in the total summation, and f of b are multiplied by h over 2, and they're pulled out front of the integration. I should say the summation. This is all process of integration. The summation goes from 2 to n, which is actually kind of the n minus 1 point, or because it's talking about the nth interval. That just evaluated f of x times h. So this part seems exactly the same as rectangular. This is the only difference talking about trapezoidal method. And it does make a little bit of a difference, because really what you're doing, if I can find a nice graphic, let's get into Simpsons a bit too quick, is weighting all the endpoints. So since each one of those summations takes the left and right hand endpoint at the same weight, then the first element in the whole list will be weighted once. Every one of these intermediate boundaries actually gets counted twice in the total summation. The very last one is just weighted once again. So the formula works out down to that given in equation 913. If that wasn't clear to you, that'll be very clear once we do Simpsons, and they have some nice graphics describing what is actually going on. So Simpsons methods are really where things start to become accurate. They're the first time you start to be able to account for curvature. Everything preceding is an averaging method. It's a midpoint method. It's essentially a first order curve fit integration. You're just taking a slope which ends up giving you the midpoint area, and it's a straight line between 2 points. If it's a tiny step size, then that's fine. If you're discretizing it thousands, if not hundreds of thousands of times, that's fine. But sometimes you either don't have the available data to do that, or you don't have the computational time to run that many points. So enter Simpsons methods for getting better total integral evaluations with fewer functional calls. So the first method is Simpsons 1/3, and that's reference for the fact that it has a 1/3 coefficient in front of the final formulation. But really what's going on behind the scenes in Simpsons is that you are assuming a second order polynomial fit. So that's a Newton polynomial with coefficients alpha, beta, gamma. Notice that each one of those is reference to alpha is just a constant, beta is the first order reference, and gamma is the second order reference, namely because of x minus x1 and x minus x2 being multiplied by gamma. So these have all been solved for their values. If you go through and just evaluate alpha, beta, and gamma as shown there in the text in the highlighted region, you can obtain the definitions exactly. That's because the coefficients have to make the polynomial pass through the given points exactly. This is not a least squares fit. This is a Newton polynomial that will pass exactly through those locations as specified. So if you know all these functional outputs, which you should if you were given a data set that you're trying to integrate, and if you have a standard step size of h, then you just use the direct definitions of alpha, beta, gamma. But it actually gets even a little bit easier than that. Once you go through the process of plugging those definitions back into the source equation 915, you're left with this definition 916. So the last formulation of it, where it's h over 3 times the functional evaluation at A plus 4 times the functional evaluation at the midpoint plus the functional evaluation at B. This weighting of the 1, 4, 1 endpoints and the midpoint, I should say, of all 3 points involved, is the core output of Simpson's rule. Now this, of course, is for a single element. And as I said, always do composite elements. So you'd again take the integration of region 1, integration of region 2, integration of everything else, and you put that into a series summation. And this is where we can start being a bit more intelligent about how we add things up. So the overall sum has coefficients 1, 4, 1. But you see in this composite Simpson's 1/3 rule, you have h over 3, so that's where the 1/3 comes from. You have 1 times the functional evaluation at A, which is the leftmost point. 4 times the functional evaluation at, well, 2, 4, and 6. Multiple points. It's kind of weird. Explain in a minute. 2 times 3, 5, 7. Again, multiple points. And then 1 times f of b, which is way over here on the right-hand side. And the way this stacks up, and the way it works out, is that you end up in doing these regional integrations. Integration 2, 4, 6, 8. They go by, I guess, even numbered integrals, but you end up weighting the leftmost x functional evaluation once, the midpoint 4 times, and then critically, the functional evaluation x3 is used twice in the overall composite evaluation. So where these coefficients are overlapping, you end up including that twice in the summation. So really these overall weightings go 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So really only the endpoints are counted once a piece, and then it just alternates between either the interior points being weighted 4 times or the boundary points being weighted twice because, well, they're involved in actually 2 different integrations in the total overall region. So that's why the definition for Simpson's 1/3 rule has one summation with a leading 4 and another summation with a leading 2. That's how it's building up simultaneous integrations of every region, and this allows you to apply that summation to all of the data you have available at once and not bother with looping through different references and doing 3 points at a time. You just apply that to the whole data set, and it works for any number of points with a couple requirements. The subintervals have to be evenly spaced, basically meaning constant step size h. That is inbuilt and ingrained into the derivation of those coefficients. The number of subintervals, not points, subintervals, so the spaces between the points must be an even number. If you think about it, that's kind of obvious because it requires 3 points to do Simpson's 1/3, 3 points to make a second order polynomial, and 3 points have 2 intervals between them. So it has to be a number of overall points that can be divisible by 2 regions. If you have, say, 1 extra point that doesn't fit that circumstance, the practice is to basically use trapezoidal rule to account for that 1 outlier. Like if you had 1 additional point out here to the right-hand side of all of that data, you'd use trapezoidal rule to take care of the straggler, and otherwise use Simpson's 1/3 for everything else, because it's just a superior method. In the same line of thought, if you're going to do a polynomial fit and then integrate that and save the coefficients in this large process, why not use cubic? So that births Simpson's 3/8 method. Again, named such because the final summation is led by a 3/8 coefficient. The polynomial of interest is given here, of course, unknown coefficients multiplied by x cubed, x squared, x. That's the 3rd order polynomial fit. The poly must pass through the data points given at all 4 locations. And you go through the same summation, the same description to arrive, which they don't cover in as much detail, to arrive at the weighting coefficients given here. So whereas Simpson's 1/3 rule had 1, 4, 1 coefficients, this rule now has, if you look up at the top, 1, 3, 3, 1. So 4 total input coefficients to make your cubic equation that you're fitting, all multiplied by 3/8 times h, thus to the name. And then the interior components are 1, 3, 3, 1. So in the same logic, when you start stacking these integrals for a composite total integration of a large data set, and you stack the 1, 3, 3, 1 weightings, it is only the exterior points, the periphery points, that remain at 1. All the interior points to each integral are weighted 3 times, and then because they are counted in 2 different integration regions, the boundary points are weighted twice. So you get this pattern emerging: 1, 3, 3, 2, 3, 3, 2, 3, 3, 2, 3, 3, 1. And that can be emulated in code through the summations given down here. And once that's done, you can apply again this integration method to a large set of data all at once without having to loop through subintegrals the entire time.